Hi everyone, for today's lesson, we are going to learn how to sketch polynomial functions in factored form. The key word here is sketch. Graphing means that you know exactly the ordered pairs to plot throughout the whole entire graph. However, sketching means that you'll make a general graph of what it in general would look like, but it's not going to be exact. Our learning objectives for today means that is for you to be able to say, I can use x-intercepts and their multiplicity and end behavior to graph polynomial functions. Now, there's some vocabulary words that I want to make sure that I emphasize with you guys because they come up throughout this unit, and I want to make sure that we're all on the same page with our vocab words. So these are terms that we've talked about before, but it's important and imperative that you understand what each of these words look like and how they are used. So, the first term that we have is a factor. And a factor is a parentheses with an expression inside. So like whenever we've factored polynomials before, we have always factored using parentheses. So like an x minus 5 and an x plus 2, both of those are considered factors because they are inside of parentheses. So for example, we have f of x is equal to 2x, x minus 5 times x plus 1. The factors of f of x are any piece that contains a variable. So it's all of the pieces that are being multiplied together. The expression 2x is a factor because it contains an x. X minus 5 is a factor because it has parentheses around it, and it is a whole quantity that is being multiplied by other quantities. And finally, x plus 1 is considered a factor of f of x as well. All of these pieces are being multiplied together to end up equaling f of x. Next, we have a 0. A 0, once again, represents the solution of an equation or the location on the graph, where the graph crosses the x-axis. Those are called zeros, and those are whenever we set our parentheses or any term containing x equal to 0. So if we were to set 2x equal to 0 and x minus 5 equal to 0 and x plus 1 equal to 0, and we were to solve for x, we would divide both sides by 2, and we would find that x equals 0 is a 0 and solution of our equation. X minus 5 equals 0 means we would add 5 to both sides, and we would end up with x equals 5 as a solution or a 0 of the function. Or if we were to add 1 to both sides, subtract 1 on both sides, we would end up with x equals 1 as a 0 or a solution of the function. So the way that we express zeros is to set x equal to a number that would make this polynomial function equal to 0. And where y is equal to 0 or where a function is equal to 0 is where it crosses the x-axis. So if I were to draw a quick sketch of what this would look like, I would have an x-intercept located at -1, 0, and positive 5. And because it's an odd function, I would be going through and having this graph go through all of those x-axes, and they would represent the zeros of my function. Finally, we have an x-intercept. And an x-intercept uses the zeros, but an x-intercept represents an actual location on the graph. And so locations we always write as an ordered pair. So although it has parentheses like a factor, and although it has the same exact values as a 0, we always write it as an ordered pair. So our x-intercepts of this function are going to be located at 0, 0, 5, 0, and -1, 0. They represent the x-intercepts of our graph. the actual locations where the graph crosses the x-axis. So hopefully this will help you clarify whenever I'm asking you to find to factor. You leave your answers in parentheses. If I'm looking for solutions or zeros, solve the equation, you would write x equals. If I'm specifically asking for x-intercepts, you would write your answers as ordered pairs. Another term that I want you guys to be aware of before we get into sketching these functions is a word called multiplicity. Multiplicity refers to the number of times a zero's associated factor appears in the polynomial. So what this means, which is very, very fancy language, it means that if you see something like a parenthesis squared, like an x minus 1 squared, and then an x plus 2, like y equals this, there is a multiplicity here indicating that this degree is actually going to be a degree of 3. So if we had just had x minus 1 squared, that's a quadratic function. But as soon as we add x plus 2 as an additional factor, now this becomes a degree of 3 based on the fact that we have one parenthesis that is being multiplied by itself twice. And that's called multiplicity. And so multiplicity has meaning, and we're going to be working with that meaning as we sketch. So it says you can use x-intercepts to sketch polynomial functions. So what you do first, whenever you are given a function, is you first identify the x-intercepts. Remember, we write x-intercepts as ordered pairs. And because of the way that the parentheses are written, it's going to be the opposite of what we see on the inside. So the opposite of a minus 2, that is a positive 2. So positive 2, 0 is an x-intercept. The opposite of a plus 1 is a minus 1. So I'm going to write negative 1, 0. And finally, negative 4, 0. And the first thing that we're going to do is we're going to plot these x-intercepts. So I'm going to plot plot 2, 0, negative 1, 0, and negative 4, 0. After I plot my x-intercepts, the next thing I need to do is I need to analyze the degree, whether or not it is an odd degree or an even degree, and whether or not it's positive or negative, and then identify the end behavior. So let's go ahead and look at the degree value. Your degree value is if we were to FOIL out all of these parentheses, what would we end up having? Would this be a quadratic? Would it be a cubic? Would it be a quartic? We need to know. Here's a shortcut. Take the exponents of all of your parentheses, which in this case, the exponents are all 1, and add them together. 1 plus 1 plus 1 is equal to 3. Our degree value is 3. Our degree is 3, which is an odd number. Our leading coefficient is the number in front of the parentheses, which is the number 1. The number 1 is a positive number. So we are going to be graphing a positive odd function. Now remember that a positive odd function behaves just like a positive linear function. So if you draw a really quick sketch of a positive linear function, our end behavior is going to be as x approaches positive infinity, our graph is pointing up. F of x, or actually in this case, it's called y. Y approaches positive infinity. And as x approaches negative infinity, that's looking at the left side of the graph, we have an arrow pointing down, which means that our function or our graph is approaching negative infinity. So how we use end behavior is this. We know that so what we do is we work with the first and the last x-intercepts, and we draw in our end behavior. Make sure it looks curvy and not like a zigzag straight line. All of these functions are not going to be zigzag, so don't do that. You want it to make it look kind of like a curvy ass looking. So I know that my end behavior means that I have like my arrow at the very end is going to be pointing down, and my arrow over here is going to be pointing up. And what you're going to do is you're going to cross through and go through all of our x-intercepts. So anytime that you have a multiplicity of 1, you're always going to cross through your function. And you'll go as high up or as low as you want to go because these are sketches. The reality of this graph is it might go up a little bit higher, it might go down a little bit lower, but what I'm looking for is that you're crossing. And because each of these parentheses are raised to the first power, what you should see going through each x-intercept, if you were to just kind of like block it off, it should appear linear going through each of these ordered pairs. You should have linear behavior going through each of these x-intercepts. So you want it to be linear, but you also want it to be kind of curvy too. So these are just going to be guesses, sketches. What I want you to also notice is the number of turning points. How often does it turn? Well, we cross and then all of a sudden it has positive, 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 increasing, and then all of a sudden it goes decreasing, decreasing, decreasing. Oh, and then all of a sudden it goes increasing, increasing, increasing. How many turning points do we have? Well, turning points is where suddenly the inflection changes of our graph. And in this case, we have 2 turning points. All right, so long story short, if the factor is linear, then it is called a linear zero, and the graph crosses through the x-axis at that point. So if we have a parentheses that is raised to the first power, the graph is going to cross through that point. Let's go ahead and look at example number 2. For example number 2, we want to sketch y equals negative x minus 2 squared plus x plus 1 squared. So the first thing that we're going to do is we're going to go ahead and identify the x-intercepts. And remember, it's going to be the opposite of what we see on the inside. And the opposite of a minus 2 is a positive 2. So positive 2, 0. And then the opposite of a plus 1 is a negative 1. So negative 1, 0. And I'm going to start off by graphing these ordered pairs. So here is negative 1, 0. Here is 2, 0. So we only have 2 x-intercepts in this problem. Next, we want to identify the degree value. Now, just like before where we added all of the exponents of our parentheses, we're going to add the exponents of our parentheses here. And they're both 2. And we know that 2 plus 2 is equal to 4. So our degree value is 4, which is an even number. Now what we want to do is we want to figure out if our leading coefficient is positive or negative. And in this case, because we have a negative 1 in front, we are dealing with an even negative type of problem. An even negative polynomial function. So if you were to do a quick sketch of a quadratic that is negative with a negative a value, this is what our graph is going to look like. And we're going to analyze the end behavior. As x approaches positive infinity, that's looking to the right of the graph, we have an arrow pointing down towards negative infinity, and this function is called y, so we're going to call it y approaches negative infinity. And as x approaches negative infinity, that's looking at the left side of the graph, we also have an arrow pointing down. So we're going to say y approaches negative infinity, and we are going to be using that information as we draw our graph. So the very beginning and the very end, which in this case we only have 2 x-intercepts, they're going to have our end behavior. So I'm going to draw like smooth curve arrows going through these points. And I know that in the very end, and my end behavior is going to be down, down. I just need to figure out what's going on in between. Now, in this problem, because we have ourselves a degree of 2 for both of these parentheses, what I want you guys to do is if the factor, the parentheses, is quadratic, then it is a quadratic zero. And the graph bounces off the x-axis at that point. So just like up here where we had linear x-intercepts, we crossed, and it was, if you did just a quick snapshot, it kind of looks linear going through each of those points. Here, it's going to bounce, which means it's going to go down and then up and then down again. At each of these x-intercepts, we're going to have what looks like quadratics, where the x-intercept is going to be like the vertex of that parabola. Like it looks parabolic right here, and it looks parabolic right here. So it's going to bounce off of the x-axis. So it has to go down and bounce, but it can't just keep going straight down. Somewhere it has to turn back around so it can bounce off of the other x-axis. So just be, or the other x-intercept. So if you see that your parentheses is squared, these are going to be bounce points. So it's going to be quadratic looking. Now, in this problem, we have 3 turning points. Turning points are where all of a sudden the graph changes directions. So it's increases, reaches this point, and then it bounces, or it changes direction. And then it goes all the way down, and all of a sudden it's decreasing, but then it turns again and it reaches a maximum point, but it doesn't keep going, it bounces again. So in this case, we have 3 turning points. This one we had 2 turning points, and look at that. Our degree was 3, and it had 2 turning points. This one had a degree of 4, and we had 3 turning points. Now there's a relationship here between degree and turning points. Do you see it? How do you go from 3 to 2 and 4 to 3? Well, you subtract 1. 3 minus 1 is 2. 4 minus 1 is 3. So the maximum number of turning points is going to be your degree value minus 1. Your degree value minus 1 represents the maximum number of turning points that a function could have. Let's talk about that a little bit more. What I have here in the next 2 problems are solo questions that I would like you guys to please complete before I see you next time. We will discuss those when I see you in class. Next, let's go ahead and extend on that idea of turning points. Now, many polynomial functions do not have what we call an absolute maximum or an absolute minimum function. And because a lot of the graphs keep going on to infinity or negative infinity in both directions, one direction, etc. Instead, they may have what we call local maximums or local minimums. And those local maximums and local minimums just represent, the y-coordinates of those represent the turning points of the function. So local maximums and local minimums represent, or those y values represent the turning points. Notice we're talking about maximum and minimum. And when we talked about maximum and minimum in our last unit, we were always looking at the y part of our vertex. So for some of these, we're going to be looking at the y part of where the graph kind of looks parabolic, identifying what that max value is or that min value is. So if you are given an equation, the other thing is, how do you know the number of turning points that you have? Because a lot of times there's a lot of crazy looking functions. Just because it has a degree 4 doesn't mean that you're going to automatically have 3 turning points, or if it's a degree 3, it doesn't mean you're automatically going to have 2 turning points. Instead, we analyze this using a maximum. So let's say that you are given an equation. The maximum number of turning points possible is going to be your degree of that function minus 1. So if you are given an equation and you want to analyze that equation and decide how many turning points it could have, take whatever the degree is and minus 1. So in this example, it says What is the maximum number of turning points that the graphs could have? Well, let's go ahead and look at the degree. Well, the key word here is could. It doesn't mean that it does. It just means that it could have. So in this case, the degree is 4, which means 4 minus 1 is 3. This could have a maximum of 3 turning points. Doesn't mean that it does, but it could. For letter B, it looks like our degree is 3. So 3 minus 1 equals 2. There will be a maximum of 2 turning points. And this degree is 5. 5 minus 1 is 4. So there is a maximum of 4 turning points. It doesn't mean that there is. We'd actually have to graph it. We'd actually need to analyze it. It would need to be in factored form, or we would have to create a crazy table in order for us to really graph it and analyze it. But this is generalizations, and in general, the maximum number of turning points that a graph could have is its degree minus 1. Let's say you're given a graph. That graph, as we've seen after we've analyzed different graphs in our previous lessons, the graph might appear to be even or might appear to be odd, and it has all of these bouncing points and x-intercepts, etc. But we don't know if it's a degree of 7 or 3 or 5 or 4. We don't know what it is, but we can tell, and that's just because of the behavior in between the graphs and the number of x-intercepts. So, long story short, the generalization is this. If you are given a graph and you want to decide what is the least degree it could possibly be, it's going to be the number of turning points plus 1. So you take the number of turning points that you see where the graph is changing direction, and then you add 1 to it. So if we look at letter A, we have 1 turning point right here where it completely changes direction. And then we have a turning point up here, so that's 2. This one right here is like a point of inflection. The graph is still decreasing. It doesn't automatically go back up. So this point is just a point of inflection that you're going to study more once you get into pre-calc and calculus. But it's not considered a turning point because the graph is still decreasing. It's not until it reaches this point down here that it is suddenly changing direction. So we go down and up, turning around, up, turning up, changing. So there's 3. So 3 plus 1 is equal to 4. The least degree that this function could be is a degree of 4. It could be a degree of 6. It could be a degree of 8. So we just know that it is even because our end behavior is up, up, and it's the number of turning points that we see plus 1. Let's go ahead and look at letter B. This function has a turning point down here where it goes down, 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 reaches a minimum, a local minimum, and then it switches direction, reaches a point up here, and then it switches direction and goes right back down. So in this problem, we have 2 turning points. 2 plus 1 is equal to 3. So this least degree could be a degree of 5, could be a degree of 7, we don't know. The degree that it could be would be a degree of 3. The least that this could be is a cubic function. This one, the least it could be is a quartic function, but it could be something else. Let's go ahead and move on to the next page. So in this problem, we are going to estimate by analyzing this graph each of the turning points and state whether each corresponds to a local maximum or a local minimum. Then we're going to estimate all real zeros and determine the least degree that the function can have. So let's go ahead and identify our local maximum. A local maximum is where it appears as if the graph has reached like a peak and then it changes direction. So our local maximum right here, this is going to be a complete approximation. It looks like we're not quite making it to -1. It's just before that. So why don't we call that like -0.75? And then it goes all the way up 1, 2, 3, 4, and a little bit. So why don't we call it 4.25? It doesn't look like it's quite halfway. So we're going to call this local maximum -0.75. Excuse me. And it goes all the way up to about 4.25. Let's look for our local minimum, and that is where it's parabolic and it reaches like this low point before it switches directions again. And it looks like this local minimum is located at about +1 and maybe a half. So 1.5, and then it goes down about a half. So it looks like it's about +1.5, comma, -0.5. So it's going to the right 1.5 and down. These are all approximations. We are estimating. We are going to be talking about in future lessons like how we can identify the exact value using technology. But for these types of problems, we're just kind of guessing at what we see. Next, we want to identify the zeros, since remember that the zeros represent where the graph is crossing the x-axis. So let's go ahead and zoom in and analyze where we think that these zeros are. So looking at this graph, it appears that this first zero is located at -1, and it's almost to -2, so I'm going to call it -1.75. Now, because this is a zero, I am not writing it as an an ordered pair. I'm just going to write it as -1.75. There are other zeros that I'm going to be writing down, so let me go ahead and analyze this again. It looks like definitely +1. It looks like a zero, so I'm going to write x equals 1. And then we have, looks like just before 2, so maybe 1.75. So I'm going to write x equals 1 and x equals 1.75. And it looks like these are the 3 zeros of our function. Now, analyzing this graph, we want to identify the least degree. And the least degree is based on the number of turning points plus 1. So I see 2 turning points here. I'm going to add 1 to it. So I'm thinking that this least degree is 3. Let's make sure this makes sense. We have arrows pointing in different directions, so I would anticipate that my least degree would have to be an odd number, for sure. I don't think it's going to be 4 or 6 or 8 because of that, but I could see it being an odd function because of our end behavior, and the smallest that it could possibly be would be a degree of 3. What I would like you guys to please do now is complete the solo, the pair, and the team questions based on the information that I have taught you in this lesson. For the very first problem, it says create a polynomial function that has 3 x-intercepts with the following end behavior. And I want you guys to look at what's happening with y. We have y approaches -infinity, y approaches -infinity. So that is your clue that we are talking about a very specific type of function. It has 3 x-intercepts. And I want you to explain why your polynomial function fits these parameters. You might be asked to write an explanation in homework or on a quiz or test. So I want you guys to make sure that you feel comfortable with explaining in words why your polynomial function meets these parameters. When you write out your explanation, make sure that you include terms like leading coefficient, degree, end behavior, multiplicity, x-intercepts, etc. And use those terms in your explanation. The next one says, write a polynomial function in standard form. So standard form means no parentheses. So standard form that has a maximum of 4 turning points. So I want you to really think about what type of function you would have if it has a maximum of 4 turning points. What would that degree be? And finally, it has what is a possible equation for the graph shown, and explain how you know. So I literally want you to analyze the x-intercepts, the end behavior, and write a possible, not meaning that it actually is, but a possible equation for this graph shown, and explain how you came up with your answer. That is the end of today's lesson. If you have any questions over anything, please feel free to email me. Otherwise, I hope you have a wonderful day.